I gave this talk last year at JS Vienna, and it was actually more. It's really high level and kind of much more abstract than probably would be good for this group. But we didn't have any talk, so I thought I'll just do it again. And I'll try to put it in the context where it makes more sense for reason, but it's still really high level. So if something is too slow, just tell me and I'll speed up, I guess. I'll start with a quote that I started the first talk with, and it's from Coding Horror, who's like a really famous blogger guy. He's the founder of Stack Overflow and kind of known in the community. And basically he said that any application that can be built in JavaScript will be built in JavaScript at some point. But I don't think it's quite true anymore. So if we fast forward to today, the quote is about 5 years old or more. I think it was quite true then because Node had such a hype and everybody was kind of going to JavaScript that it was quite true at the time. But now things have changed with going sort of meta, with having TypeScript, having Elm, having different sort of influences into the JavaScript world. And the meta part is that we're taking another step further in sort of the abstraction and maybe trying to abstract away some of the things that are not so great for humans, but for machines they're still not necessary. And this makes, the language is not restricted by where it's supposed to run anymore because it runs actually on a different language. It's compiled by the Babel compiler or whichever one to another runtime. So it gives us sort of freedom to do more things for the human and still be able to deploy to the machines. And this is a completely different point, but if you look at Facebook, which started with PHP, and they basically have PHP and C++ mostly. But it's not like your grandma's PHP. It's like super sophisticated with typing and everything. They have code that changes code. And basically, I talked to one of my friends who works there now, and he goes, well, if you want to go fast, so they're trying to go fast and break stuff. He's like, if you want to go fast, and even if you're trying not to break stuff, you need typing because it just makes everything safer. It makes it more easier to change code and evolve and maintain code. And the other thing that's coming from different things now at the moment, which seems to be a trend, is the developer experience, like with Elm, better errors and stuff like that. So summing up, I think we're past the point that everything's going to be built on JavaScript. It's kind of going in a different direction. But let me go to something completely else for a second, to music, into the domain of music. And this is really, it's been bugging me for a long time, why there's this myth that a lot of good programmers come from music or have a musical background. And it seems that there's some kind of skill set that helps you programming when you are in music. So let's take a look at music. Music is very fast-paced. It's actually changing all the time. There's something new basically every day because every musician has their own style and something else to contribute. There's trends that matter. Like, for example, blues was a big thing, right? It was a huge trend that came into all kinds of things. It's open source by nature because if you have an ear, then you can understand the other people's music and you can try to emulate it. So you learn it actually sort of by reading open source. And it's highly dependent on the hardware. So if I play a song on an electrical guitar, it's way different than on a classical guitar. And the other thing that's interesting is that usually it's performed by people who have a different skill set, a lot like programming, where you have teams that are sort of intertwined somehow, but also as individuals very different. You can have an analyst in a team with a designer. So how is music taught? It's actually, I really like this picture because of the sort of cultural, mix. But basically, it's not taught like this. It's not taught as a broadcast. It's taught actually mostly by radio or just by listening. Kind of like this open source thing. You just listen and you try to do the same thing with your instrument. And if you think about it on a high level, even more so actually, because this is taken from the movie School of Rock, if anybody's seen that. So the evolution, it's these groups influencing each other. And so just anybody who knows anything about modern music, blues and jazz is kind of the foundation, and then all these other things like country. Country was kind of on the side, but funk, rock and roll in the end, all these things came out of those styles, and it was just a iteration every time, basically, and they added like one small element, and it became this new thing. And so it's just kind of interesting how it's kind of like spread through communities, just like programming. And communities come up with new things, and then they influence another community, and so forth. And it's just like a forest. It keeps kind of growing. So changes are usually small and incremental. But sometimes there are huge game changers. I kind of touched on it before. The electric guitar changed sort of everything, actually. Not because the instrument was so new, but the things that you could do with the electric guitar was just like paradigms higher than with the guitar before. It completely changed how even guitarists are viewed. Like the solos. Of course, you had solos before, but it's not like, big hair and sort of rock and roll type of stuff. So that was a huge paradigm shift. So let's get back to the programming languages that we kind of, let's see how that worked in tech. In tech, we started really low level. I think the first programming languages were mostly shaped by not maybe the best ideas, but by how the CPU worked. So these people were trying to figure out how the machine works, right? So they were very low level. Okay. And they were mostly imperative, so it was like command, 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 and at the end I get something out. Then things started changing a little bit with Smalltalk, I guess. That was the first one that tried to manage state a little bit differently. It wasn't anymore imperative and then go to somewhere else, but they were trying to shape the program differently, and ML was at the same time around. So this was also when the mathematical, kind of interesting. I'll come back to it later, but I think the first languages were not necessarily shaped by the mathematical ideas that were around already, but more by the things that were possible with the machine. Then was an interesting time, right? C++, really huge, still around, still kind of imperative, but more into classes and stuff, object-oriented. And then came the 90s, which was really interesting, where some of the functional stuff, that's when the math kind of met the tech, or the CPU guys met the math guys, and they said, wait a minute, we can do some things better maybe. So these things, and if you think about Python and Ruby, they have really both influences very strongly. Same with JavaScript, both sort of object-oriented and functional. And then some of the more modern things that we know and use now. And still, there seems to be a balance, Some are more on the object-oriented side, some are more on the functional side. And there is reason, so let's see how it continues. So is it like a battle? Sometimes, like for me, it felt like a battle because functional programming felt so different from it was like way better, right? But in the end, I kind of figured out it's just different things. And there's good things and bad things in both of them. One of the really bad things, I think, about object-oriented is that it's sort of easier to misuse. So this code is kind of really, it's not really object-oriented, but it's a valid code in the object-oriented language. This was written in JavaScript, could be in C# the same, could be in Java. But it's kind of like I declare something, or I make this something that I'm going to mutate, and I do a lot of stuff to it. But don't worry about it too much, about reading it. I want to show you what I did to it. So I took this code, and I was actually working on it, and I did it first in functional. So I did it like this. It fits basically on one page. I just extracted some functions that I needed. And so the nice thing is, I think about functional is that you kind of declare the stuff that you need as functions, and at the end you kind of compose it together, and you get this thing out that it's supposed to do. So here I just used an array that had all these strings inside that were, before it was like every line was a new string, right, adding to the string. And here I put everything into one thing, and I sort of filtered and mapped it, and then I got out what I wanted. So here you can, actually it's quite readable. I filtered out the non-empty things. I removed the slashes with a map, and I joined it with a dot, which is what I was trying to do. So in that sense, it's kind of elegant in object-oriented, but it also has some downsides that, in functional, but what I'm kind of trying to get at is that both have downsides and upsides, strengths and weaknesses. And so this is the object-oriented part, where I created an object that was the application name, and it has some properties. It was pre-ES6, so I had to use prototypes, but basically it's an object that has these properties, and then it has some logic to sort of put it together at the end. So it's not that much different, actually. It's just that it's a bit different how I had to structure it. I had to put properties instead of functions, and everything is kind of in one context. That's, I think, the strength of object-oriented. In the other example, I had some functions that were sort of generic, but you didn't know the context. You didn't know necessarily that it was about a name. It was just about a string, or maybe just about an integer. So at context, object-oriented is much better. Okay, I need to go back. I should have maybe summed it up a little bit here, because I'm going to jump into a new thing. But was it clear from the example? What are kind of the strengths and weaknesses? Okay, so now I'm going to talk more about what happened for us as an industry. And I split into backend and front end because it's really way different what happened. So in the backend, the evolution was to scale it out horizontally instead of getting bigger boxes. So when I started in programming, the only way you could get something faster was to add CPU or RAM, basically. You could only get a bigger computer. You couldn't really scale it out because there were VMs, but it was just so clunky and you couldn't really define the OS very well. Or at least it wasn't as far as it is now with Docker and all this stuff. So this has really become way easier, and I think that had actually a huge influence on how we program, because we scale differently. So Java and JVM was really designed, or it was really good at squeezing all the juice out of the sort of the box, because you could tweak it, you could add RAM here and there. So if you had just one box and you had to get everything out of it, it was perfect actually. It was really powerful at that. But the functional paradigms are way better for stateless things, because the way that you handle state is really explicit, and you have to think about it, and you have to sort of be aware of what you're doing. In the front end, it's a way different story. So this was the front end that I remember, where everything was kind of cluttered, and it's kind of the same story. You have one application that has everything inside. You didn't have Google Docs where you collaborated with other people. It was just running on your machine. And you kind of had all the features in there that you kind of could dream of. And then gradually with the web, things started to get, again, sort of horizontally scaled, because you had small features, small UIs, linear UIs. And with the apps, I would say even more so, because you really have, in this case, the Messenger and Facebook. There could probably be 10 more for Facebook, where you would have really specific use cases inside of one app. But anyway, it seems that it's also kind of scaling that way. So just to kind of summarize what I said before, the other thing that I kind of said implicitly, there's a lot more devices, so the space is now so different, and the space on the mobile is way different than on desktop, and so you have different problems in UI than you had in the 90s. And the state in front-end applications is also a big deal now, because like in Google Docs, it can be sort of distributed even between people or applications. You have the suite of Google things, and maybe there's some things that need to be everywhere and some things don't. So it's become way complex. Not sure how to transition now to this one. I should have probably put it way later, but it's not really viewable, is it? No. I didn't put a link on it. I will simply explain it. So the whole point of this slide, or this image, which is taken from this Pete Van Roy who did a lot of work on it, because this is only one example that he has on his website. There are lots of others. But basically, he's trying to sort of summarize the paradigms that are out there. So kind of a map to the things we have. And on the left side, so the red things are really like functional declarative, like Prolog, stuff like that, if you know it, or I don't even know most of them, or haven't really used them actually. Stuff like the query language, which is really like pure functional, or sort of in the middle is, anyway, I don't know anyone's on the left side, so that's like way abstract, way mathematical. In the middle you have Haskell, Alice, OCaml is sort of also in the middle, which has from both sides, you could say. And then on the right side, on the way right, are the really imperative and or object-oriented things. But again, the point of this slide was kind of to go back to the musical thing. It's like these things have influenced each other, you know. It's not the same way like blues influenced jazz maybe, but kind of, you know. There were ideas that were spread and changed, and it's just been a thing that's evolving. And what I try to show with the evolution of the programming languages is that kind of object-oriented and functional were both an answer to imperative. Because in imperative, they couldn't really manage the state very well. So those were both kind of approaches to how can I manage the state well. And make it into small chunks. They were like trying to go away from this jumping inside of the code and having more structured things to sort of support the application. And so summing up the things about the strengths and weaknesses, I think object-oriented is actually better at context. It's sort of easier to model something in the real world than in functional maybe. But at the same time, some of the things are not so reusable because they're really tied into their context. It's very flexible and open if you think about it, because an object can be anything. You can sort of model it really to your sort of desires or needs. And but because it's so open and sort of flexible, it needs to be managed with patterns like we see from the books and everything that's written about it. So I think this openness creates a need for structure. And in functional, you basically have that kind of built-in because you have the functions as sort of generic building blocks. And on the other hand, you need to manage the context. It's not clear in this example that I showed. The context was not clear, kind of, not even from my comments, unless you saw that one function where I put everything together. Yeah, more reusable chunks, and it's kind of more rigid actually. If you think about it, it's not, the patterns are not open, they're kind of built into the language. You have to sort of know them and use them as they are. This is kind of a metaphor that I like to use because I work now with lots of applications across the board, and they're all kind of running in production, but they need to be maintained. And I feel like a diver. So it's like when you're looking for this bug and you don't know, it's like you're going in and everything is kind of blurry and you don't really see. You have your little flashlight, but there's like a huge ocean. So I feel like when we write the code, we don't actually think about this moment where we have to dive in. Like the maintainability is not something that's on our mind. And so readability is a big deal. I feel like with functional, it's a bit more readable. It's more declarative. You can kind of show the things that are going on better. But at the same time, the context is also really important because if I don't know the context of the bug, then it's a lot harder to find. So it's what I'm kind of trying to get to is that there are really good things in both of them, and we should just do it sort of think about what we want to use for the use case. But in the end, they both kind of give you reusable blocks. You just have to kind of, I think in object-oriented you have to be a bit more structured and disciplined. In functional, you have it already built in. You have sort of these functions that are the small blocks. Okay, so now actually I get to the real talk that I gave last time. So the mathematics part. In mathematics, it's really different because in mathematics, you don't have a machine that calculates, or at the time when they were coming up with these things, they didn't have machines, they didn't have computers. So they had to think really, really abstract, like this thing, n plus 1. Okay, what is n? It can be a real number, it can be an integer, it can be an imaginary number, right? And depending on which data type it is, there are different rules that apply even to this statement. So they have to really think very abstract. And what the mathematicians use or came up with is sort of set theory, where they have sets of numbers, which can even be infinite in lots of cases. Or they seem, there's no boundary, but it's just, basically it's an array of numbers that can be infinite, a set. And then out of this set theory, so what I'm trying to get to is the sort of the computation theory, but it all started in mathematics. And I can't really say this for sure, but I mean, the problems that they had to solve was, you know, like, unless you had really lots of money, you were working for somebody. And what was going on like 200 years ago, there was wars mostly. That was probably like the biggest money maker. There was some business and stuff, but I don't think mathematics had so much appliance there. So lots of the people that made the breakthroughs either were really interested, they were rich and they could use their time to work on it, or they worked for someone who, you know, gave them like, solve this, I don't know, attack on England. How can we do it better with shooting our whatever? No, it's just a stupid example, but I think they were trying to look for sort of shortcuts. So how can I, you know, find a solution that I cannot use a computer to compute it. I need something abstract that I can prove. So they were looking for proofs for sets or proofs for different things. How can I prove that? And they came up with this, which is part of the set theory. And if you look at it, I already put in the sort of more programming things that we know. So if you look at it, you know, you have a set of A's, something, and then you map it to a set of B's, something. And then maybe you have a set of B's, and you rearrange it somehow, like sort or reverse it completely, and you have another set of B's. So these were the problems that they were sort of thinking about. And the other thing that they had was the logic part that started also way before computer came. They already knew how to sort of infer. So if just an example, this is actually Prolog. This is regular Prolog code. So if it's kind of like defining rules, and then based on the rules you can get something out of the program. So you can define a person, which doesn't tell us anything except that it's true or false. Either there's a person or not. But then it gets more interesting because you can, for example, define the parents, and you can define siblings, what a sibling is. So somebody who shares the parent, of course. And if you had a much larger set, you could make all kinds of assertions based on these rules. So those two things, the set theory and the logic part, were, I think that's where they were headed in the computational direction. And I always like to put the Kaiser in my presentations, but in this case it has a specific reason, although I sort of foreshadowed it already. So most of the people that came up with these things were actually like born or alive at when the Kaiser was still our governor. And there were no computers, so even the Kaiser could have been a computer theoretically, because a computer by definition is a person or a machine that executes an algorithm. Okay, so the first guy that was kind of trying to find a breaker was David Hilbert. He did lots of things in mathematics, and basically he was trying to find like the algorithm of algorithms. So to define some really fundamental rule that would help him make his job a lot better. So if he had that rule, he could really sort of show that computation was possible for almost everything. And he was looking sort of for that definition of the algorithm. And he came up with the halting problem, the Entscheidungs problem, which was really big because basically that means if it was true that it was possible, if the Entscheidungs problem was provable then or applied to everything, then they would have just one formal definition for all calculations. So they could say that a computer with infinite RAM and CPU could calculate anything in the world. But this is not true, because afterwards came Kurt Gödel, who was Austrian, and he proved that it's not complete. So the entire set of mathematics cannot be proved to be calculatable. So basically there are some things that you can't calculate, no matter how big the machine is. And he proved Hilbert wrong by formally defining this. And what he did was that he said that this statement is not provable. He wrote it down as numbers. You can somehow translate words into numbers. And he had an equation that was, you could calculate it, so that it was just numbers, but it showed that you cannot prove it. So that kind of showed a hole in the system. And if there's one hole, then the whole system breaks down in mathematics. So basically, he showed that Hilbert's sort of across-the-board definition would never be true, which made a lot of mathematicians very sad because they were always looking for that one definition. I already said that, but it does not mean that the subsystem cannot be complete. So you can define axioms for a subsystem of numbers or things that can be complete. And that's where a lot of the church comes in with his lambda calculus. And basically the lambda calculus is complete and is sort of almost a programming language. There's a funny story to it. So Alonso Church defined lambda calculus and showed it to Gödel. And Gödel, the good Austrian that he is, he said it's wrong. Of course, it has to be wrong. It didn't come from me, so it has to be wrong. And then Gödel said, and then Church said, well, you come up with your own definition, and we'll see where we get at. And Gödel came up with the recursive functions, and then Church proved that they're equivalent, so it's the same work, just I think defined in a different sort of, one was logic and one was calculus, so defined in a different thing. And upon hearing that, then Gödel said, well, then mine must be wrong too. So, yeah, we have the pessimism in our blood, I guess. And this is typed Angular. This doesn't tell me that much, but I looked, for example, in JavaScript. And if you look at it, it's got all functions, right? So, I mean, it's kind of understandable if you think about it for a while. But basically, it's just composing functions all the time. It's kind of really funny. So you could program with lambda calculus, but it would not be very readable. It would just be a bunch of functions. So this code actually increments whatever you put in by 2. I didn't run it, but it looks like it could work, I guess. Here you have the incrementation by 2, I suppose. But yeah, you can sort of Google or GitHub for examples if you like. And then, but there was still kind of unsureness if it's really correct what they said. And then Turing sort of settled everything with his machine because the machine could also prove that some things are not calculable just by showing it actually physically, because it would simply stop calculating if you had an invalid calculation. And Turing was so Church was his teacher and they worked together a lot. And they defined it completely then. And all of a sudden you had three things that were correct and the same thing. Just sort of, I didn't really understand it until I read it today completely. So the breakthrough with the Turing machine was that you could have a Turing machine that operates on another Turing machine. A Turing machine you can think of as a program because it has the ability to read or write onto a tape. And that's basically it. But still, on one Turing machine, you would define like a few steps, and then it would just do that. It would still be not a breakthrough unless he found out that he can actually sort of program that one program. So he can work on read and write on that one program. And so it was like a meta thing. And that's where this Turing completeness comes from. The funny thing is that apparently it's not possible even with a modern computer to calculate more than with a Turing machine. Although it's really simple. Okay, and then the last missing piece is Haskell curry. There's a programming language for his first name and his last name, by the way.
And he has a middle name too.
Ah, really? Okay, nice. Uh-huh. But he worked in a pair with Howard. And through this correspondence, they came up with lots of things where it's even sort of too high for me to understand. But basically, what they came up with is that if you write a, it's on the next slide. If you write a program in some complete system like Landau calculus, then it's actually proof that it's computable, so that you can rely on getting a result from a machine. So that was kind of the link from the Turing machine to more modern machines. Yeah. Okay. And to come back to a point that I said earlier, so I think that lots of things that we see didn't necessarily have to do with the mathematical development that I showed, but like how the programming languages evolved had much more to do with the hardware evolution, actually. I mean, if you think about it, they only had this, right, in the beginning. And then they started to build more complex machines. And then somehow with Turing was the breakthrough to have a machine operate on a machine, sort of on a program. And after that, you had, I guess, for this room, as big as a room computers that didn't have any RAM and all this stuff. So I think the early machines, early programming languages were sort of tailored to that use case of not having RAM and CPU. And then as the computer evolved, the programming languages got a lot more sophisticated as far as they could. I'm kind of trying to set the stage on where we are now. Yeah, this is a branch. I maybe should. So coming back to, it's the first time I'm giving it, so I'm just realizing that I'm jumping a little bit too much. But coming back to object-oriented versus FP, there was a talk just a few days ago on the Go to Chicago by Anjana Vakil, and she's been interested in functional and stuff for a long time. And I like the talk, but she used as a sort of metaphor for OOP, she used cells, which is what the inventor of object-oriented LNK kind of described it as cells. So he thought there are kind of cells that have a context and they talk to each other as messages. But when I first saw that, I thought, I've never seen an object-oriented program that does that, actually. It's more like spaghetti, in my experience. And she used the metaphor for functional programming as being a factory for cars, for example, where you have functions, that have like one sort of thing, like putting on the wheels or putting on the color, and you sort of compose it together on this conveyor belt of actions. But I kind of went back to these things, and I thought about it. It didn't really strike a chord with me. I thought it's kind of a good metaphor, but it doesn't really explain what I understand on the difference. And I came up with this other sort of metaphor that object-oriented is a lot like a car. So I put it into the context of movement, of moving people. And with a car, you kind of have this autonomous thing that is able to go on all kinds of different surfaces. It can go on a road, or it can go off-road, or it can go on a mountain. It can go kind of anywhere. It's really flexible and also kind of powerful, but you can't really scale it very well because you either get a lot of cars or you get a lot bigger car. And if you have a lot of cars, then the overhead of sort of managing them is really high. And if you get a bigger car, then you have a physical sort of constraint. You can only go so big. And I think functional programming is a lot like a train. So it has these sort of things. You have to have a track. It's more rigid in that way. You have to have some certain rules, but you can scale it a lot better because you can add, for example, just wagons, or you can replace a wagon with another wagon, or you can add, the Lokführer, whatever the first car, or the last car. And in that way, the scaling part is a lot more flexible. So, having now given the context of history, what can we sort of look forward to? What are the options that we have now? So going back to the paradigms, we can still combine more, maybe. Maybe we can come up with sort of more different flavors of languages. Or David Nolan in his talk last week called for sort of newer paradigms, so maybe adding to those, maybe thinking more outside of the box and adding to that mix. But either way, in terms of paradigms, I think it's worthwhile spending time to learn new ones, because whatever's going to happen, it's either going to morph, so grow with the stuff that we have, or there's going to be new stuff. And the question is, what is the next electric guitar? What is the next really big thing in computing where we have to be able to react to it? And so again, I kind of go back to the hardware, and actually a lot of this comes from the conversations that I had with Nick, with how the cloud is now scaling. So the problems that we have now are a lot different even than from 2 years ago. We kind of solved the scaling part because you can very easily instantiate stuff in the cloud. But there are also lots of things that we haven't solved yet. So what will be the next game changer? We have to kind of look. Actually, I'll do this one first. That's the question. How will the infrastructure evolve? Is there still going to be cloud? It has some good sides. It has some bad sides. It has lots of problems with the startup speed. And on the application side, there's also still lots of things that are unsolved. In terms of logging and tracing, I think it's still kind of weird that it takes me like so long to find a bug, although we have all this sophisticated infrastructure and stuff, and it's hard to track down still. The tree shaking bit. So again, I think the sort of way forward will be that infrastructure and application will sort of morph more together, it seems. And for that, the applications have to become leaner, sort of this tree shaking thing. We see it in the front end, and we see it in the back end as well with Mirage OS and stuff like that. But the funny thing is, the cloud is now actually the single point of failure. If it goes down like the AVS, then you're still screwed, no matter how great your application is. So still lots of questions. And now, what can Reason offer for that? So actually putting the context on this meetup. I think the compiler is definitely a good thing, because it seems that the transpiler times might be, evolving into compiler times, where the compiler gets much smarter. And like I said, they're going closer to the native, because the problems that the cloud has now can only be solved by actually slimmer applications. So going closer to connected, slim applications. Mirage OS, as we saw in the talk last time. And it's kind of taking the VMs out of the picture. So, the VM basically is just another big framework, if you think about it, that's in the middle of your application and the hardware. And the other thing that Reason offers is this, it's functional by default, but not closed. You can use different paradigms, so giving you the full set. And in the front end, it's a good addition to the JavaScript, I think. And that seems to be definitely a trend with TypeScript and Elm, like I said. And maybe, hopefully, it will add to the React sort of ecosystem, let's say. But definitely there's lots of room to grow, and it's sort of interesting, I think, to stay on Reason and see how it evolves. So I will just sum it up. You don't have to be a great electrical engineer to come up with a hit song, but it definitely doesn't hurt if you know your instrument a lot better. So I think investing time in learning stuff is a good thing. And I purchased this book about a year ago, and a long time I didn't get started reading on it. But it's if you want to it's written by a programmer, but he goes through the math stuff. So it's kind of understandable, but some chapters I skipped because it was too high for me. But some, like the Turing Machine, and the name is Good Math. And I think he also has a blog, but the book is really cool. So if you're kind of looking for sort of what is he goes through the broad spectrum. So what are the things how did the numbers get started, and how does that come into computing? And like I said, some chapters you can skip, but overall it's a really good read. Yeah, so that's it, actually. Thanks for your time.